Welcome back everybody to Calculus 2. In the last unit we covered 5.2 in which we found the volume of cross-sectional areas with our Calculus 2 knowledge. Today we are going to be taking a look at work and how to find work with our Calculus 2 knowledge. But first we want to know the definition of work. We define the work done in moving an object from A to B as W equals the limit as n approaches infinity of the sum from I to n of f of x sub I times delta x, which we can reduce and simplify that to simply the integral from A to B of f of x dx, where f of x is our function of force. It's our equation of force. So we also want to look at Hooke's law, because Hooke's law is going to be important for this. Hooke's law states that the force required to maintain a spring stretched x units beyond its natural length is proportional to x. That is, f of x equals k times x, where k is a positive constant. Another thing we want to take a look at is the theorem of finding the cross-section of a liquid. It says if lowercase sigma is the density of the liquid, d of y is the distance to where the liquid is being pumped, a of y is the area of a cross-section of liquid perpendicular to the y-axis, and the liquid exists between y equals a and y equals b, then work equals the integral from a to b of lowercase sigma times a of y times d of y dy. So that is your theorem on work for a liquid. So now that we've covered all the important information, let's get into some practice problems. So in this first problem, we are told that a 360-pound gorilla climbs a tree to a height of 20 feet, and we're asked to find the work done if the gorilla reaches that height in A, 10 seconds, and B, 5 seconds. So the first thing that might help you when solving this problem is to just draw out what's going on. So right here, I'm going to draw a tree, which will just be represented by a line, and you can just imagine that that's the tree. So we know the gorilla is climbing to a height of 20 feet, which means he's going to end 20 feet in the air. Because the problem didn't specify that the gorilla started climbing when it was already on the tree, we can assume that it's starting at the ground, meaning he's starting at 0 feet. So the gorilla will be moving from 0 to 20 feet. So right there, that's the distance that I know I'm going to use for my bounds of integration. So for this first problem, let's use 10 seconds. So I'm going to write work equals the integral from a to b of f of x dx, where f of x is the force equation. So like we just said, the bounds of integration are going to be 0 and 20. And so now we have to find the force equation. If you remember from physics, force is equal, let me write this down, force is equal to mass times acceleration. We're given that the mass of the gorilla is 360 pounds, so this is going to be 360 pounds. Now the acceleration is going to be a little bit trickier to figure out, but it requires just a thought process. So we know that the gorilla is going from 0 to 20 feet in 10 seconds. It doesn't specify that at some point during the tree he starts going really fast, or at another point in the tree he starts going really slow, meaning that his velocity will his change in velocity will remain constant throughout his climbing of the tree, meaning his acceleration is going to be 1, because he isn't accelerating. He's moving at the same velocity all throughout the tree. So that's our force equation. F of x equals 360 times 1, which is just 360. So I'm going to write down 360 dx. Now when we go to integrate this, it's going to be 360x, and we're going to be evaluating it from 0 to 20. And so if we were to take the derivative of 360x, we would get 360. So the antiderivative of 360 is 360x. Now if we go and evaluate this, it's going to be 360 times 20 minus 360 times 0. Now 360 times 20 is 7,200, and 360 times 0 is 0. So we have 7,200, and let's look at our units here. 360 is the mass of the gorilla, meaning it's the pounds, and the 20 is the feet that he traveled. So it's 7,200 foot-pounds, which we said was a common unit when dealing with force. So we know that at least we're on the right track with our units. If your units don't make sense, then you might need to rework the problem. So that would be the answer for him climbing the tree in 10 seconds. 7,200 foot-pounds of work. If we do it for 5 seconds, I'm going to go ahead and rewrite the integral down here. So our bounds of integration are still the same. He's still climbing from 0 to 20 feet. So when we write our force equation, we need to realize that this is also the same, because his mass is still 360 pounds, that doesn't change, and his acceleration, it doesn't say that he's accelerating at any point. He's climbing the tree at a constant velocity, meaning his acceleration is again going to be 1. So the force is going to be represented by 360 yet again. Now at this point it's completely identical to what we did over here, so I'm just going to skip all those steps of work and write that again 7,200 foot-pounds of work were done when the gorilla climbs the tree in 5 seconds. And that would be your final answer for that one. So in this next question we are told that a variable force of 5x to the negative second power pounds moves an object along a straight line when it is x feet from the origin. Calculate the work done in moving the object from x equals 1 feet to x equals 10 feet. So let's just write out our work equation. So we know that work is equal to the integral from a to b of f of x dx. And f of x is going to be our force equation, which we're given is represented by 5x to the negative 2 power. So I'm going to write the integral from a to b of 5x to the negative second power dx. And they also tell us that our bounds of integration are 1 and 10. So I'm going to plug that in right there. Now when we go to find the antiderivative, I know that there's going to be an x in there, and I want a number in the exponent that when I subtract it by 1, I will get negative 2. And so if I think about it, I will realize that that number is negative 1, because negative 1 minus 1 is negative 2, which is what I have over here. Now that I need to think, what can I multiply negative 1 by to give me this positive 5? And I will realize that that is negative 5. So if we were to take the derivative of negative 5 times x to the negative 1, we would get 5x to the negative 2, which is what we want. So this is our antiderivative. I'm going to write this in a simplified form though, and I'm going to write it as negative 5 over x, because that negative 1 exponent means it goes in the denominator. And that is going to be on the bounds from 1 to 10. Now all I have to do is plug in those bounds in for x, and when I do that I'll have negative 5 over 10 minus negative 5 over 1. Negative 5 over 10 is the same thing as negative 1/2, and negative 5 over 1 is the same thing as negative 5, but because of this minus sign here, they become an addition, so it's plus 5. Now if I want to get this into equal or like denominators, I can write this as negative 1/2 plus 10/2. And then when I solve that, I will get 9/2. And this is going to be foot-pounds again. because the distance we're moving is feet and our force is measured in pounds. So that would be your answer for that one. So in this next question we are told that shown is the graph of a force of function in newtons that increases to its maximum value and then remains constant, and then we're asked how much work is done by the force in moving an object a distance of 8 meters. So on the x-axis here you see our distance of meters, and on the y-axis you see our distance in newtons. And so you can see the graph seems to go up for 4 meters, or it seems to increase in newtons for 4 meters, at which point it reaches the maximum number of newtons, which is 30, and then after that it remains a constant 30 newtons for 4 more meters. Now the thing to realize here is that the answer is simpler than it might seem at first, and what you need to realize is that newtons times meters equals joules, and joules are a unit of work. We can measure work in joules, meaning that in order to find the work done here, all we need to do is find the area under the graph, which might make sense because we've been doing integrals, and integrals after all are just the area under the graph. But in this one we don't even need to set up an integral. We can take the much easier route of finding the area geometrically, because we have a triangle and a square, or a rectangle. So we can find the area of the triangle, or the area of the triangle, and then the area of the rectangle, and add them together. So the area of the triangle is going to be 1/2 times the base, which is 4, times the height, which is 30, plus the area of the rectangle, which is the base, times the height, and the base is 4, and the height is 30. Now I'm going to bracket these off so we know that they're separate things. So 1/2 times 4 is going to be 2, and we're going to have 2 times 30, and then 4 times 30 is 120, so we have 60 plus 120, which is 180 joules. And that would be our answer for that one. Okay, so in this next question we are told that a force of 10 pounds is required to hold a spring stretched 4 inches beyond its natural length, and then we're asked how much work is done in stretching it from its natural length to 6 inches beyond its natural length. So the first thing we want to notice here is that it's talking about a spring, which means we want to be thinking about Hooke's law. And remember that Hooke's law says that the force required to maintain a spring stretched x units beyond its natural length is proportional to x, meaning f of x, which is our force equation, is equal to k times x, where k is going to be a positive constant. And we know that the force is 10 pounds, and we know that it's being, we know that the 10 pounds is required to keep it stretched 4 inches beyond its natural length. So we're going to put 4 in for our x, and then we're going to solve for k, which is our positive constant. So we have k equals 10/4, which if we divide the numerator and the denominator by 2, we're going to get 5/2. So we're going to set up the regular work integral now. So that's going to be work equals the integral from a to b of f of x dx. And so now when we're solving this, we want to think about what our bounds of integration are. And we're going to be going from 0 to 6. And the reason that is because we're stretching it from its natural length to 6 inches beyond its natural length. And our f of x is going to be 5/2 x. Because remember, our f of x equals k times x, and we found that k equals 5/2, so we can rewrite that equation as f of x equals 5/2 x, like this, 5/2 x times d of x. Now let's think about the units we're using here, because that will help us figure out whether or not we're on the right track. So this 5 over 2 here, this 5 is coming from when we divided 10 pounds by 2, so we have pounds in the numerator, and then we have 2, which is coming from 4 inches divided by 2, so we have 5 over 2 pounds over inches times x inches, because we're going to be stretching at a certain amount of inches. So then we can cancel this part out, and then when we get there, this d of x is also in inches because it's a change of it's a change of distance, so it's in inches as well. So then what we have is the integral from 0 to 6 of 5 halves x pounds inches, or pounds times inches. And now with some conversions here, we can get this into foot pounds or pound foot. It's commutative, so it could go either way, because inches, 12 inches is 1 foot, so this could easily be a foot pound. So, and we said that a foot pound is a measure of work, so we know we're at least on the right track here. So now I'm going to set up this integral. So when I find the antiderivative of 5 halves x, I know that I'm going to want a squared in the exponent position so that I can bring it down and then subtract the 2 minus 1 to get x raised to the 1, which is what we have here. So now I need to find the coefficient here, and what we'll find is that it's going to be 5/4. So if we were to drop down this 2, it would cross reduce with the 4 and we'd get 5 halves. So 5 halves x squared from 0 to 6. I'm not going to solve for 0 because that would just be 0. I'm only going to solve for when x equals 6. So we have 5/4 times 6 squared, which is 5/4 times 36, like this, and then I can cross reduce this and it becomes 9, like that. And then so I can do 5 times 9, and I'll get 45 pounds over inches. And now I can do some conversions, and I know that there's 12 inches. Oh, sorry, I messed that up. This is going to be 45 pounds times inches. And then now I can do some conversions here, and I know that there's 12 inches in 1 foot. So these inches units cancel out, and 45 divided by 12 I believe is 3.75. So we get 3.75 foot-pounds. Foot-pounds. And that would be your final answer for that one. So in this next question we're told that suppose that 2 joules of work is needed to stretch a spring from its natural length of 30 centimeters, which is 0.3 meters if we're working in SI units, to a length of 42 centimeters, or 0.42 meters. So we're asked first to find how much work is needed to stretch the spring from 35 centimeters to 40 centimeters, and how far beyond its natural length will a force of 30 newtons keep the string stretched. So I'm going to start with part A, and the first thing I'm going to do is write out delta x. This is going to be our change in x. And what we're going to be doing is we're going to be going from 0.42 minus 0.3. This is the amount of meters, that it's from 0.3 meters to 0.42 meters. That's how much 2 joules of work is stretching this spring. So that's going to give us 0.12 meters. Now after that, I'm going to write out my work formula, which if we remember is work is equal to the integral from a to b of f of x dx. And now from there we're told that what's needed is that 2 joules of work is needed. So right here for W, I'm going to substitute in the 2 joules of work, and then I'm going to write my integral here. And because we're going from the natural length, which is 30 centimeters, to the non-natural length, or the second length, which is 42 centimeters, we'd be going from 0, which is the natural length, to 0.12, which is the amount of meters that is being stretched. So the lower bound of integration is 0, and the upper bound is 0.12. Then I'm going to rewrite just the f of x d of x. Now, if we think about it, our f of x, our force formula, is just k of x, like this. So what we're going to have is 2 equals the integral from 0 to 0.12 of k times x dx. And remember, k is a positive constant, and x is the distance, or how much is being stretched, I suppose. So if we solve this integral, or if we write out the antiderivative, we're going to get 2 equals k times x, and this x is going to be squared, and the k and the x are going to be over 2. And the reason that is because k is a constant, and then so when we find the derivative of x, the derivative of x, or the antiderivative of x, is 1/2 x squared. So think about it like this: we would have k times 1/2 x squared, and then we can just simplify it by writing it this way. So it's just a simplified version of finding the antiderivative. And then we can write from 0 to 0.12 again. And then so if we go to solve this, we have 2 equals k times x squared, or I suppose I can substitute in the 0.12 now. K times 0.12 squared over 2. And I'm not going to solve for this 0 because it would just be 0. So then after we do that, we say 2 equals k times 0.12 squared, which is 0.0144, 0.0144 over 2. Now, because I'm trying to get k by itself, I'm going to multiply both sides by 2. And I'm going to get 4 equals k times 0.0144. And then at this point, I can divide by 0.0144 on both sides. And I get k equals 277.78. Now at this point, I'm still not finished, so I'm going to erase all this work up here, so make sure you have it written down. So at this point, I'm going to bring this up here. And now, this is still part A, by the way. Now I'm going to rewrite the work formula, but this time my lower bound of integration is going to be 0.05 meters, and my upper bound of integration is going to be 0.1 meters. And the reason that is because our natural length is at 30 centimeters, right? But it says that we're starting at 35 centimeters. So at the time of us stretching the spring, it's already been stretched 5 centimeters, or 0.05 meters. And we're stretching it to 40 centimeters. And 40 minus 30 is 10 centimeters, which is 0.1 meters. And then again, I'm going to write the k times x d of x. And we know what k is now. Because k is a constant, we know it will always be 277.78. So I'm going to write 277.78x dx. And now when I go to do the integral of this, when I go to evaluate the integral, this x, when we do the antiderivative of x, we know that there's going to be a squared in the exponent position, it's going to be like that, which means we need to half this number, because if we were to take the derivative, then we'd bring this 2 down and multiply it by whatever was in here, which would be 138.89. So again, this is the antiderivative, because if you would take the derivative of this, you would get 277.78x. And our bounds of integration are once again 0.05 to 0.1. And now if you were to solve that, if we were to write it out, it would be 138.89 times 0.1 squared minus 138.89 times 0.05 squared. And now if you were to do this all out on a calculator, you'd get that the answer is 1.04. So that would be your answer for part A. But again, we are not finished there, so we still need to keep going. So in part B of the question, it says how far beyond its natural length will a force of 30 newtons keep the spring stretched? So I'm going to write out Hooke's law. F equals k of x. We know that the force is 30 newtons, and we know that our k is 277.78. And now all we need to do is solve for x. So we do that, 277.78. Our answer, we should get, I think it's, let me do this on a calculator. I had it written out, but I lost that spot. 30 divided by 277.78 is going to give us 0.108 meters. So that would be your answer for that one.